Hi. So today is the second lecture on the one space dimension heat equation. And let me tell you what we're going to do. We're going to go through two examples from our textbook, Edwards and Penny. Where we use Fourier series to solve a type 1 and a type 2 initial boundary value problem. And as we talked about in the last lecture, the idea is to use superposition of product solutions of the form a function of x times a function of time. Which works because this is a homogeneous linear PDE. Ut equals k uxx. Partial of u with respect to t is a constant times partial of u with respect to x. And then finally, after all the hard work, we'll go to Desmos and demonstrate the solutions that we worked out. Okay, so to warm up, do you remember what the type 1 and type 2 initial boundary value problems were for the heat equation? So remember, we're looking for a function u of xt defined for x between 0 and L. And for x between 0 and L and t positive, it's supposed to satisfy ut equals k uxx, which is the partial differential equation describing how heat diffuses either through a one-dimensional object or in a one-dimensional way through things like walls, which have higher dimension. And you start with an initial distribution of heat. And then, which we call f of x. And then the BV of the IBVPs is the boundary values, and those have to do with what happens on the endpoints of your rod when x equals 0 and x equals L. And so for type 1 was the fixed temperature, which by adding a constant and also potentially subtracting a linear function in x, we always study in this class where we fix the temperature on both endpoints to be 0. So type 1 was fixed boundary temperature. And type 2 was the no flux boundary condition. And we're always assuming that if it's a rod, the lateral sides are insulated and heat can only escape out through x equals 0 or x equals L. And we know that the heat flow is proportional to the gradient of the temperature. And so the no flux boundary condition is that du dx at 0t and du dx at LT are always 0. Okay, and in the last lecture, we studied product solutions of the form a function of x times a function of t. For the function of x for type 1, we had to get, and this was an eigenvalue problem, as you recall, for the second derivative linear operator. We had to get that the x functions were sine of n pi over Lx. That would make them 0 when x is 0 and when x is L. And then the t function that you had to multiply by to get a solution to the heat equation was e to the minus this coefficient, this angular frequency, which was also the eigenvalue, minus n pi over L squared times t. And let's just, we already figured out sort of from first principles how to come up with these, but now that we have them, let's just check. So if this is my product solution, a function of x times a function of t, then u sub t is, well, the x part is just a constant, computing that partial derivative. And then when I take the derivative of the exponential, I'll get the exponential times the coefficient of the t in the power, which is minus n pi over L. Oh, I forgot the k in the solution. So it was minus that thing squared times kt. Okay, so now let's go back and with the correct power in there. When we take the t derivative of the exponential, we will get the exponential times the coefficient of t. Okay, now let's compare this to, oh, and I got the minus sign in the wrong place. Let's compare this to k uxx. Well, if I take kuxx, I'll be taking two derivatives of the sine term in the product, and, well, I'll have the k, and then when I take two derivatives of the sine, each time the chain rule, well, when I go from sine to cosine, I'll get an n pi over L. Then when I take the derivative of that, I'll get a factor of minus n pi over L. So I will get a minus n pi over L squared when I take two derivatives. And then it'll come back to sine n pi over Lx e to the minus n pi over L squared kt. And if you stare at these two things, the ut and the kuxx, you'll see that every single term matches up now that I've remembered to put them all in. And so that's a summary of where we got those special product solutions from. And then for type 2, the special, and these were like indexed by the number n, the product solutions were of the form cosine n pi over Lx times the same exponential and we don't have to go through the same check. You can just see if you take partial u with respect to x of those things, the cosines turn into sines, and because of the n pi over l's, when you plug in 0 or L, those sines will evaluate to 0, so you'll satisfy the no flux boundary condition. Okay, so today we are going to build up from these product solutions to do two interesting examples. I took them right out of the text. They're good examples, plus because we're good at rescaling our 2 pi periodic short list of examples, we can get our solutions much more quickly than the text does. So let's look at the first example, which they call example 2. We have a rod of length L, which is 50 centimeters. It is immersed in steam until its temperature is uniformly 100 degrees Celsius throughout. And then at time t equals 0, we embed either end into ice water, which has a temperature of 0 degrees Celsius. And the lateral sides of the rod are insulated. So now we're supposed to find the temperature that solves the heat equation and calculate the rod's temperature at its midpoint half an hour later, and we're supposed to do it for the diffusivity constants of iron and concrete. Okay, so this is a type 1 fixed boundary temperature problem, and we have two different Ks. Presumably the temperature is going to diffuse faster through the iron rod than through the concrete rod. Okay, so for type 1, what we're going to want to do, since we have fixed boundary temperatures, so the let's draw the axis for the actual rod. It's going to go from 0 to L. The initial temperature is going to be U0, which will be 100. And we want to do the type 1 problem where the temperature at the boundaries is always 0. Obviously, at t equals 0, something weird is going on because we put the ice water in, but this actually makes sense. So in any case, we want to do the odd extension of that function, which will give us a sine series. Okay, well you can see this is just a rescaled square wave. So what we're going to do is use that rescaling from the square wave to get the Fourier series, the sine series, for our initial temperature distribution. So the square wave goes between 1 and -1 as its x values go between minus pi and pi. Okay. Right, so let's just record some information here. Eventually, we're going to plug in numbers, and our U0 is going to be 100. Our L is going to be 50. And we'll be trying to solve ut equals k ux x for 0 less than x less than L, t positive. U of 0t equals U of LT equals 0 for t positive, and our initial temperature distribution is just U0 all along the rod. So f of x is U0 for 0 less than x less than L, and minus U0 for negative L less than x less than 0. And we're using the odd extension because we want a sine series in x so that the temperature is 0 at the endpoints. Okay, so let's stare at this picture. So let's try to relate f of x to the original 2 pi periodic square wave. Well, in the x variable, we're scaling the interval from 0L down to the interval from 0 to pi. So if we take the square wave of pi over Lx, then as x goes from 0 to L, the pi over Lx will go from 0 to pi, which is exactly what we want. And then in terms of the function, we want temperature U0 instead of temperature 1. So that is f of x defined in terms of a rescaling of the horizontal and the vertical axes back to the square wave. And so we can just do the Fourier series for f by taking the Fourier series for the square wave and plugging in pi over Lx wherever the x's used to be. Okay, so we now have the Fourier series for the initial temperature distribution in example 2. And now let's write down the solution. And this is just an infinite dimensional version of what we were doing in the last video. So in the right-hand corner here, I've rewritten down the heat equation and our product building block solutions. And from the last page, I have pre-copied the Fourier series for f. And it's always wise to triple check. Yes. Okay, so then the game we played in the last video was, this is supposed to be, f of x is supposed to be u of x 0. And the way we get u of xt is we just turn every function of x into a function of x and t, where t equals 1, the coefficient is 1. And we did it like this. So u0 4 over pi sum over n odd 1 over n sine n pi over Lx. Okay, so now I've just written down u of x0, but I'll multiply by this exponential e to the minus k n pi over L squared t. And at t equals 0, that's just 1. So u of x0 definitely has the same Fourier series as f. Each one of those building block product solutions solves the heat equation with 0 values at x equals 0 and L. And because the heat equation is homogeneous, sums of solutions are solutions, and so waving our hands, infinite sums, convergent infinite sums of solutions are solutions. And so that's u of xt, and let's see that it's the same as what the text told us. So the only difference is they took the n pi over L quantity squared, and they rewrote it as n squared pi squared over L squared. So those are the same. Okay, now, and so here we have the table of diffusivity constants. Remember, the larger k is, the more ut reacts to k times uxx. So larger k means poorer insulators, smaller k means better insulators. Okay, now in the text, there is a graph of what happens. This is for the first thing they wanted us to use, which was iron. So this was a diffusivity of iron. And let's have a look at that graph. So you can see the initial temperature is 100 all along the rod, and then because the ends are dipped into ice water, T equals 0, that keeps the temperature 0 at the end points. And as T increases, more and more heat is getting sucked out of the rod, and that's why you get this kind of parabolic profile picture of what the temperatures look at later times, and they're all going down. Okay, so it is true that in this problem, the maximum temperature of the rod will always be at its midpoint. I know how to prove that, but it's not that easy to prove. Anyway, it looks to be true, and it is true, and it's steadily decreasing. Both of these can be proven. So now they have a formula for the temperature at the midpoint, which is x equals 25, which is L over 2, because L was 50. They have a small typo, which I highlighted. This should give you an alternating series because you're only summing over n odd, and sine of n pi over 2, that starts out as sine of pi halves, which is plus 1, then sine of 3 halves pi, which is minus 1. So that actually alternates like minus 1 to the n plus 1 over 2 for n odd, but that's the only typo I found. The u naught was 100, so 4 u naught is 400. The exponential, yeah, you can work that out. But I'm not going to. I checked it. So the sine n pi L over 2 over L worked out to those plus or minuses. And, oh, that's, yeah, okay, so T is 1800 seconds. And anyway, that's related to the L squared, which is 50 squared. And this turns out to be right. Okay, so now they're doing it for iron. And we were supposed to estimate the temperature after 1800 seconds, which is 30 minutes. And when you look at that series, you get an alternating series. And because of that exponential term, which decays very rapidly as you increase n, essentially the first term is everything in the alternating series. And so the temperature after 30 minutes is about 44 degrees. Well, 43.85 degrees Celsius. Okay, now in part B, figure not shown, although if you look at the formula for the solution, you can see that changing the K just corresponds to scaling the time. So in a way, what it is shown here, but it's just the very first part of the graph when you rescale the time. Anyway, with this smaller diffusivity constant for concrete, the alternating series is not all contained in the first term, and you have to go through, the text goes through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms, and yet when they add that alternating series up, they get essentially 100 degrees Celsius. So with concrete, in half an hour, almost no cooling in the center. And if you've ever lived in a brick house with thick walls in a hot climate like Salt Lake City, you know this phenomena, because in the middle of the summer, it might have gotten up over 100 in the daytime, and your house might have felt nice and cool during the day, even with no air conditioning. But then around 1 or 2 o'clock in the morning, because the heat finally got through the walls, your house starts getting unbearably hot, especially if you're in the second floor of a 2-story building like I live in. Okay, so that's example 1. Now let's go to the second example we're going to do, which is the text's example 3. It's still a 50-meter rod, but now we're going to have a different initial temperature configuration. It looks suspiciously like the tent function, rescaled. And we are going to do a type 2 problem where we insulate the ends. So we need the use of x's to be 0 at x equals 0 and L, and so we're going to do an even extension and get a cosine series. And so let's have a look at this interval from 0 to 50. If we do the even extension, we actually get exactly a tent function on the interval from minus 25 to 25. That's our friend, the tent function. It's just been rescaled. Okay, so the textbook goes through some fairly nasty rigmarole to recompute the Fourier series, but we don't need to because we know how to rescale. So let's do it. It's still not easy. So let's draw down the 2 pi periodic tent function. Its period is from minus pi to pi instead of minus 25 to 25, and it's the absolute value of x just like the other one, but that causes a rescaling in the vertical. Okay, so tent of x is absolute value of x for x between minus pi and pi. Let's call this function here, they called it f of x. Okay, so we can do that. So f of x, although we care about the interval from 0 to 50, it's really the 2L, where L is 25, tent function expanded. So it's actually 4 absolute value of x, because at 25 it's 100 for negative 25, oops, less than x, less than 20. My fingers want to write pi instead of 25. Okay, whereas tent of x is absolute value of x for x between minus pi and pi. So let's try to write f of x as a rescaled tent. So if I take the tent of, so this is trying to get something where the L is 25. So I will take pi over 25 times x. Then as x goes from minus 25 to 25, the tent argument is going from minus pi to pi. That's what I want. But it will be the absolute value of that, which is pi over 25. Oh, yeah, the tent. Okay. That will be the absolute value of pi over 25x as x goes from minus 25 to 25, which is pi over 25, the absolute value of x. Okay, so what we wanted was f of x. So f of x which was 4 times the absolute value of x, is it's 4 times 25 over pi times the tent of pi over 25 x. Right, so if you look up here, 25 over pi times the tent of pi over 25x, the reciprocals cancel and I'll just get a 1 times the absolute value, and I want 4 times the absolute value. Okay, therefore, f of x is 100 over pi, that's the 4 times 25 over pi, and then I just take the Fourier series for the tent of pi over 25x, which is pi over 25, sorry, pi over 2, minus 4 over pi, the sum over n odd of 1 over n squared cosine of n times pi over 25 x. That is the Fourier series for the initial temperature distribution that we wanted to study. Okay, so now let's go solve the heat flow problem. So I thought we were going to call the function g, but we called it f. And all I did to go from the green to the blue is I multiplied the 100 over pi n, so I got 100 halves is 50, and then it's minus 400 over pi squared times that. Yes, okay, so I have checked that we got the same answer on both pages. Now we're trying to solve the heat equation, and for the heat equation, our building blocks are of the form sine of something x times e to the minus that something squared times t. And so we can write down u of xt the same way we did in the first example. Okay, so constants solve the heat equation ut equals kuxx because both sides are 0. So this is like the a naught over 2 term. Then we have minus 400 over pi squared, the sum over n odd 1 over n squared cosine n pi over 25x, and I multiply by the exponential, which equals 1 at t equals 0, so that I recover f when t equals 0. Okay, now I wrote u of xt above the text's version so that we could compare to see if we got it right. And although usually I'm the one who makes typos, this time the text did. That coefficient in the denominator should be a pi squared, not an n squared. And now you might get upset over the 1600, but I can explain why they have a 1600 and we have a 400. We are summing over n odd. They got their Fourier series in a much harder way, and they're summing over n over 2 is odd. And so their n's are twice ours, and so their n squareds are 4 times ours, and 1600 over 4 is 400. So that's that factor. The cosine, and they have cosine n pi x's over 50s, but their n's are twice our n's, and so that corresponds to our cosine n pi over 25s. And it's the same deal in the exponential term. Our minus kt's agree. Their ends are twice ours, so their n squareds are 4. Right, and let's see, I see the pi squared. So with their n squared, where did that 2500 come from? Their n squareds are 4 times as much. Let's see if I made a note about that. I am not sure. So that's right. I have 25 squared, and 4 times 25 squared is 2 times 25 squared is 50 squared is 2500. Yeah, okay, so I don't know if you followed it, but actually our formulas agree, and the way we wrote it is much nicer than the way the book wrote it, and they had their typo. Okay, so let's have a look at their picture. So you can see the initial tent heat distribution from 0 to 50. You can see that in the type 2 boundary conditions, the use of x's are always 0, and as t goes to infinity, all of the terms with the decaying exponentials go to 0, and they corresponded to parts of the heat distribution that had average 0, and the u of xt will converge to the average temperature along the rod at t equals 0, which was just the a naught over 2 term. So this height is converging to 50. And in fact, all along the rod, the temperature is converging to 50. You can see it's almost gotten there. By the time we are at 1200 seconds, which is 20 minutes. And this was for the iron, which was the faster, the larger diffusivity constant. Okay, so we're almost done. There's a couple cool Desmos demos that I want to show you, but unlike in the last video, I don't want to forget to summarize what we did first. So we can solve initial boundary value problems for the heat equation, homogeneous heat equation, ut equals k u x x for x between 0 and L and t positive, with an initial temperature distribution given by a function f of x. For type 1 boundary conditions, where u of 0t and u of lt are 0 for t positive, we do the odd extension for f. That gives us a sine series. And out of that, we extend using the exponentials to extend to t positive to get u of xt. For the type 2 boundary conditions, flux through the end, so the u sub x at 0 and the u sub x at L is 0 for t positive. We do the even extension. That gives us a cosine series. And then we extend using the e to the minus k blah 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 t terms. To get the solution u of xt. Okay, and now let's go watch movies for each of these two examples. Okay, so this is the first example where the initial temperature was 100. I rescaled that down to 10. You can rescale solutions to homogeneous equations because multiples of the solutions are solutions. I did that because I don't know how to make Desmos scale the horizontal and vertical axes differently. So we care about the interval from 0 to 50, and here you can see the odd extension. I just typed in our solution with k equals 0.15. That was the iron. I have to say it's much harder on an iPad than on a computer to type in the solution. On an iPad, unless I'm missing something, it's kind of like using a graphing calculator. Okay, so remember what happened here. Because the temperature was 0 at the two endpoints, which were at 0 and 50 centimeters, all the heat got sucked out as T increased. And so you're seeing all the profiles of the surface that we were looking at in the first example. So I went up to 3,000 seconds, which is a little past where they went, and the temperature has gone down, and if we went longer, eventually at a decaying rate, exponentially decaying rate, the heat would all get sucked out. Okay, let's look at the type 2 example. So here I typed in the formula, and rather than 100 degrees at the max, I made it 5. Oh no, it was 50. Rather than 50, I made it 5. Okay, so there's no flux through the endpoints at 0 and 50, and so rather than everything going to 0, it will converge to the constant solution where the temperature is 5. And so let's watch the movie. Okay. So we're up to almost 2,000 seconds. You can see that the temperature is converging to 5 everywhere. The heat is just diffusing to the constant value. Okay. So that's a good place to stop. And you'll get to make a movie for the wave equation. I didn't assign any for the heat equation. The wave equation is going to be even funner to think about than the heat equation. But it was the heat equation that got Fourier motivated for Fourier series, so let's not sell it short. And it has all kinds of applications beyond the one we studied.